Previously in looking at capacitance, we sort of described capacitance or defined it as the ratio between the charge that is stored and the potential difference across the plates. But if you go back to in subtopic 10.2, we were looking at charge density when we've got dealing with sort of electric fields. We looked at charge density between two parallel plates, so in other words a capacitor. Surface charge density is a particular phenomenon that we looked at then that relates to what we're talking about here as well. And surface charge density on the plates is given by this equation. So surface charge density is the amount of charge over the area of the plates, and it's given by the permittivity of free space multiplied by the potential difference over the distance between the two plates. Now you might recall that this V on D is actually equal to the electric field strength between the plates, but we're not really interested in the electric field strength here. The plates are so closely spaced that we can't really measure that electric field strength, so we'll leave it as V on D instead. That means that we've got the potential difference that we can measure and the distance between the plates that we can set up in the manufacturing process. Now if we rearrange that equation, you can hopefully see that we can arrive at an expression for Q on V. So that's simply by dividing by V, taking V across onto the left hand side, and we'll multiply A up onto the other side, so we end up with epsilon naught over multiplied by A over D. So that then gives us, if we've got Q on V, we know that that's our capacitance, so we can then say that capacitance is equal to the permittivity of free space multiplied by the area over the separation of the two plates. So that's an equation that we can then use for capacitance. Now, to take this a step further, keep in mind that epsilon naught, that relates to free space, so it's the permittivity of free space. In other words, if you had just air between the two plates, if an insulator is used instead, that value is going to change depending on the substance that's being used, or depending on the insulator. So when an insulator separates the plates, that equation then changes slightly, and it basically just becomes, so I actually probably shouldn't highlight that one. It's basically then becomes that it's just the permittivity of the material multiplied by the area divided by the distance. So note here that we've got a few different ways that we can increase the capacitance by either using the, let me actually, just note these down. So epsilon here is the permittivity of the insulator, and the units there would be farads per meter, but the units of permittivity are, you'd be given what the quantity is that you're dealing with there. You can always figure it out from the equation if you need to. A is the area of the plates, and we're talking just cross-sectional area here, so it's not the total area of the two plates, it's just the area of one of the plates, and D would be the distance between the plates. And hopefully you can see there we've got those three quantities now, where we can use those to change the capacitance. So the first one to look at is that the capacitance is directly proportional to the area. So if we increase the area, basically means that more charge can be stored. And if more charge can be stored for 1 volt, then we've increased the storage capacity, and so capacitance increases. So fairly straightforward, that one. Makes sense that if you've got more space to store charge, then you can increase the storage capability, and so the capacitance will increase. Second one that's not quite so obvious is the distance. So with capacitance being inversely proportional to the distance, the reason why we get an increase in capacitance here is that if you increase the distance, or increasing the distance between the plates, there's less attraction between the oppositely charged plates. So while we've got charge building up on the plates, we've also got this attraction between the plates, and so if you've got less attraction, that means that less charge can be stored. So the closer the plates are, the more attraction there is, the easier it will be to get a few more electrons across onto the negative plate. And so with less charge separation, capacitance decreases. And finally, the last one is the permittivity of the material. So when we're looking at the permittivity, we're talking about how the substance affects the electric field between the two plates. So just make a few more notes here about this one. So the first thing is that insulators are going to affect the electric field between the plates. So if you've got a substance between the plates, because there are now more protons and electrons arranged in the molecules that are between the plates, it has an effect on the electric field between the plates. And as a result, that's going to have the overall effect of allowing capacitance to increase. Now, I know that's not really explaining why, but easiest way to explain the effect of the insulator in between is to actually refer to a specific type of insulator that can be chosen specifically to increase the capacitance further. So to increase capacitance further, we can actually use materials known as dielectrics. So a dielectric material can be used, make sure I spell that correctly. So a dielectric material will be used as the insulator. So it's still an insulator, still not going to allow current to flow through it, but what it does do is that it so the molecules in the dielectric material, they actually become polarized. So what I mean by that is that with the electric field showing what happens to positive charges, means that the molecules in the dielectric material can start to line up with the electric field between the plates, and the effect of that is that they actually decrease the size of the electric field. So I'll just draw a quick diagram to illustrate that. So for our diagram, we'll have the positive plate on the left-hand side and the negative plate on the right-hand side. So that then means that the electric field that will be established between the two plates will be going from the left to the right. So it would have an electric field that's in this direction. Now, if we were to then place a dielectric material in the middle here, what's going to happen with the molecules that are in that dielectric material? So imagine we've got the one here. If that molecule is going to align itself, and let's draw a few of them in, they're going to sort of align themselves with that electric field, so that the negative end is closest to the positive plate and the positive end is closest to the negative plate. So we're going to get that effect the whole way through the dielectric material. Now that means we've got a slight separation of charge in each one of these molecules, which then creates a small electric field in the opposite direction to the electric field produced between the plates. So by having the dielectric material in between the plates, it has the effect of decreasing the electric field between the plates. And by decreasing that electric field, it means that more charge can be stored. So decreasing that electric field means increasing charge storage capacity. And as a result, capacitance. And so three different ways there that we can increase capacitance. Some of the dielectrics that are fairly common that you might come across in dealing with capacitors, things like paper, mica is another substance, Teflon, plastics, ceramics, and even some metal oxides, so things like aluminium oxide. It can be useful in that you don't necessarily then need to put a layer between the plates. If you've got aluminium, oxidizes fairly easily, so just by having an aluminium oxide layer, that can actually act as your dielectric instead. So there's how we can adjust the capacitance or change the capacitance of a component by varying its properties, whether it's the distance between the plates, the area of the plates, or the material that we put in between the two plates.